I am Casf of second year studying in EC department of third sem. Now I would like to talk about my TikTok topic of subject complex analysis and special function. And the TikTok topic is generalized integral controllability. Now let's go to the introduction of generalized integral controllability. Generalized integral controllability is a significant concept in control theory. It extends classical controllability notions by incorporating integral constraints. Understanding the concept is crucial for systems governed by differential equations. And the definition is generalized equation is a concept in control theory that extends the traditional notion of controllability to the systems which constraints or uncertainties. The key point is system description. Consider a linear time invariant LTI system described. Y is equals to Cx plus du, where x is the state vector and u is the control input, y is the output, and A, B, C, D are the system matrices. This is the introduction to general integral controllability. Now, here comes to the basic definitions. Controllability refers to the ability to steer system state to desired final state. Integral controllability involves control inputs integral over time to achieve system objectives. Generalized integral controllability combines these aspects for more complex systems. This matrix includes the inverse of A, which accounts for constraints or uncertainties, rank condition, applications, integral controllability. Integral controllability implies the system states that can be controlled to zero or any other desired value over a finite time interval. The mathematical formulation. The mathematical formulation typically involves differential equations with control inputs. Integral conditions are incorporated in the formulation to define the controllability criteria. This leads to the analysis of reachable sets in the state space for the system. Here, the applications are constraint control systems, uncertain systems, nonlinear systems, distributed parameter systems. Theorems and results are Kalman's controllability theorem and generalized controllability theorem. Here, the Kalman's controllability theorem is a system is controllable if and only if the controllability matrix Q has full rank. And the generalized controllability theorem is a system is generalized as integral controllable if and only if the generalized controllability matrix Q G has full rank. Open research directions are nonlinear generalizations, time varying systems, distributed systems. These are the extending generalized integral controllability to nonlinear systems and developing controllability conditions for time varying systems. Investigating generalized integral controllability for time varying systems. The importance of generalized integral controllability. This concept is essential for systems where traditional methods fail due to constraints. It allows for more flexible control strategies in nonlinear and time-varying systems. Applications include robotics, aerospace, and economic systems that require precise control. Here, the properties of the generalized integral controllability are necessary and sufficient condition, equivalence to controllability, invariance under similarity, transformations, relationship to observability and stability, and mathematical properties are rank and additivity, matrix inversion, determinant, and geometric properties are reachability, controllable subspace, and algebraic properties are Cayley-Hamilton theorem, minimal polynomial. And these are the proofs and the properties of and the importance of generalized integral controllability. The key theorems and results of this theorem is several theorems provide necessary and sufficient conditions for generalized integral controllability. These results often involve rank conditions related to the system state and input matrices. Understanding these theorems is critical for applying the concept in practical scenarios. Moving on to next slide, we have about the examples of generalized integral controllability. Consider a linear system with integral control inputs for state regulation. A nonlinear example could involve trajectory planning in autonomous vehicles. Various cases studies that illustrate the application of the theory in real world situations. As you can see that it is applicable and can be seen in real world situations of generalized integral controllability. Here is an example how we can use in the mathematical way. Numerical methods for analysis. Numerical simulations play a vital role in analyzing generalized integral controllability. Techniques such as discretization and optimization can help determine the control over inputs. Software tools are often used to model and evaluate system behaviors effectively and efficiently. The eigen-based methods are eigenvalue decomposition, compute eigenvalues and eigenvectors of A and characteristics polynomial. Compute the characteristic polynomial of A and the minimal polynomial. Compute the minimal polynomial of A, singular value decomposition, and also matrix norms and measures. And also we have about linear algebraic methods, the Gaussian elimination, transform Q dash G to row echelon form, and LU decomposition, and also Kuleske decomposition, and optimization based methods. The linear programming formulate the generalized integral controllability as a linear program. Semi-definite programming formulate generalized integral controllability as a semi-definite program. Model preceded control. Use MPC to analyze generalized integral controllability. And the numerical software are MATLAB, Python, and Simulink. And the algorithms are Kalman's algorithm, Rosenberg's algorithm, and Wang-Wang principles. These are the principles and numerical methods for analysis. The challenges and limitations. One challenge is the complexity of systems with high dimensions and nonlinearity. Additionally, computational costs can increase significantly with size, and addressing these limitations is crucial for broader applications of theory. And computational costs can increase significantly with the system size. So here we can see that it increases and cost can increases significantly with the system of size, and the challenge is complexity of systems with high dimensions and non-linearity. This addresses the limitations is crucial for broader applications of the theory. These are the challenges and limitations. Now moving on, future directions and research trends. Ongoing research explores enhancing robustness in generalized integral controllability. Integrating machine learning techniques could provide adaptive control solutions. Collaboration across discipline may yield innovative approaches to complex controls. These are the future directions and research trends. And here come to the practical applications of generalized integral controllability. Generalized integral controllability is relevant in areas like telecommunications and robotics. It can be also applied in economic models where integral constraints are present. Understanding and applying this concept can lead to more efficient system designs. So these are the practical applications. And here comes the conclusion of our TikTok topic. Generalized integral controllability represents an evolution in control theory as its implications are vast and, and impacting various engineering and applied science. Continued exploration of this topic will enhance our understanding and the applications of control system. Now we come to the some of the properties and numerical methods for analyzing the controlled generalized integral controllability are eigen-based methods, singular value decomposition, matrix norms and measures, and linear algebraic methods. Linear algebraic methods are Gaussian elimination as we said before and discussed, and LU decomposition and some decompositions when we know about them, when we go further and depth of the subject. And and eigen-based methods are eigenvalue decomposition, characteristics polynomial, minimal polynomial. These compute eigenvalues and eigenvectors of A, and also compute the characteristic polynomial of A, and compute the minimal polynomial of A. Together we get the eigen-based methods value of the generalized integral controllability. The implications are vast, impacting various engineers and applied science. Continued exploration of this topic will enhance our understanding and control over the subject. So, as we know about the conclusion, generalized integral controllability represents an evolution in control theory. And here are the references from whom we got the generalized integral controllability and many other mathematical discoveries. Thank you.